All right. All right, Gabby, you want to tell me?
Yes. Yes, I have a question. I finished my lab,
Oh, good.
but I don't know if my graphs are right. They look like exactly like you said they good,
Oh, good. Okay, there's the first one. Yeah.
but they didn't meet at the origin specific like you said. But
Oh, okay. Okay, that's a good one. Let me see the last one.
okay, look, hold on. This guy.
Yeah. Okay. Good. Yeah. They. It's okay if they don't meet at the origin. They would only meet at the origin if we didn't have any friction. And so that's kind of how we analyzed it. All we did was the two weights that were hanging without the friction from the wheel. And the reality is we do have friction from our wheel. So
Right.
in a perfect world without friction, it would have gone through the origin. And that's kind of what our discussion was about. But if you actually graph them and it doesn't go through the origin, that's actually good because you're seeing the effect of the friction. Uh, you're noticing
Yes.
that there is something more going on than we analyzed.
This is the last one, the inverse mass.
Yeah. Okay, good. Good.
That's good.
Yeah, that's exactly good. That's really
All
good.
right. Yeah. So I did the numbers. So I think there are like 5 pages because there's the one that you help us answer. This guy.
Yeah,
I finished that,
good.
and then the table that we have to fill in,
Yeah, yeah, good.
and then the graph. For the last question, you kind of help us, but you didn't were specific, so I answer. If the acceleration is constant,
Yeah,
force is directly proportional to mass.
directly. Yes, yes, that's right.
If the mass is constant, force is directly proportional to acceleration.
Okay, yes, yes.
And the last one is if the force is constant, acceleration is inversely proportional to mass.
Right, right.
Okay, so I think that I'm good. What else do we have for this week? Nothing else.
Let's see. For you guys, yeah, nothing else because you just took a big test. Yeah.
Yeah, yesterday was really horrible because I had 3 tests.
Ouch.
I did. I think I was told at the beginning of the when I began in SBCC that we were not allowed to have 3 tests in the same more than one test. I can say in the same day. So I don't know what happened, but
Oh,
yesterday was horrible.
yeah. There's a school. I think there's a school policy that says if you have 3 tests on the same day, you can petition your teachers to move one.
Yes, I know. The thing is that I didn't even notice. I've been so busy with so much because I'm taking chemistry 156 and I'm taking all calculus. So they're a little bit hard classes.
Yeah.
So I've been so busy and I didn't notice. Usually the tests are usually by 11 p.m. Usually all the time, other classes. They give you a time frame, but you can do it anytime, but within 1 hour. But gotta be
Oh,
until 11 p.m. But yesterday the teacher changed the rules. He put it due to 11 to 1 p.m.
oh.
So I was hard because I had to be doing this test. It was really horrible yesterday. But
Um,
anyway, it's over.
hey, well, let me tell you this: if it happens again, you can petition any of your teachers, and I'd gladly, uh,
I did to one of my teacher, but he just didn't reply. So I said, well, I did it. And anyway, regarding the exam, I think at the beginning, what do you exactly want? Because I think this was my first exam, so I didn't know exactly how it goes. Um, I think when in the first questions I wrote too much, I think, and that wasted my time. And then by the time I said, "Oh my gosh, it's about time to finish," so I was being hurrying at the end. So the next time, I don't know, do you really want in the first questions to write
No, in the multiple choice, there it's either right or wrong. So just put the letter A, B, C, you know, and move
all
on
right,
and save
okay,
your time for the multiple choice, because that's where
yes.
I give partial credit, and yeah, and
And
there's
I
more
noticed,
points.
and I noticed too that one of the a few of the questions, the last one, they were very easy to do.
Good.
But the multiple, but I didn't have time. I said, well, I just couldn't do it. But next time I'll be more prepared.
Yeah. Okay. Good. Well, that's yeah. And then right, there is something to be learned, and that on the first test about how to take the test, and all my tests are kind of structured the same. So you you see that now, and so you've comes to me like you've learned a good strategy for next time.
Yes. All right. So okay. So homework is over. It's already done. So next week we began next chapter. So we began doing homework for chapter 7. Correct?
Oh, right. Sunday, I'll send out the video for chapter 7 and the homework for chapter 7. Yeah.
All right. That's pretty much it. Okay. Bye,
Okay.
everybody. Thank you.
Okay.
Bye.
Bye. All right. Okay, let's see. Let me set up my phone here, and I'll just say it again. Anybody from 102? I didn't see anybody there, so I'm going to move on to you guys in 123, probably. I think, Daniel, you had the first one. Let's see. Auto lock. Oh, good. It's already off. All right, let me hook up my camera here and give it some power. Switch it to video. Nice. Okay. Let's see. All right. So, Daniel, you got let's see, chapter 19, number 38, and we're looking at about 10:09. Okay. So, chapter 19, number 38. All right. Now, I think I'm going to need to call those up as well as connect my phone here. So let me do that. Share phone. Chance to connect. All right. Well, that's going around here. Let's see. Homework. Oh, good. I already got your homework already up and running. I think. There it is. Yeah. All right. So let me get to 19, number 38. All right. 38. Oh, yeah. This piston one here. Okay. Yeah. This one looked interesting when I read it. I don't think anybody's asked me about this one yet. Okay. So it says here. Uh-oh. My camera freeze already? Can't see my hand.
I don't see your hand either.
Ah, bummer. All right. So what happens? Stop sharing. Start sharing. I wonder if plugging in the power could have tipped it off or anything. I don't know. All right. Now I see my hand moving. Okay. All right, so let's read this one. Here it says a cylinder is closed by a piston containing a spring with a spring constant of 2 times 10 to the, and I need to make mine a little bigger here. Go to 100%.
Third?
Yeah, it's like a 3. Okay. With the spring relaxed, the cylinder is filled with 5 liters of gas at a pressure of 1 atmosphere and a temperature of 20 degrees Celsius. Okay. If the piston has a cross-sectional area of 0.0100 meters squared and negligible mass, How high will it rise when the temperature is raised to 250 degrees Celsius? And then B, what is the pressure in the gas at this 250? Okay, so I guess I would say that keep in mind two things that come to mind. The first one is PV equals to nRT. And so if I would apply that to the initial scenario, maybe I'd have something like this: pressure initial, volume initial equals initial number of molecules times initial temperature. And then as we warm it up, in fact, maybe I'll just put in what we do know. Let's see. The spring is relaxed, and so the spring is relaxed. The gas is filled to a pressure of. Now, they give us units in liters and atmosphere. Now, I bring that up because we have a choice of units for R. And I'm a little more comfortable using the 8.31. And then when I do that, though, the pressure is in pascals, the volume is in cubic meters, the moles is in unit of moles, and the temperature is in Kelvin. So I'm going to go ahead with that one. I know that some people like the R as point, would be 0.0, I want to say 821. Not 100% sure on that one, but that would have units of atmospheres and volume in liters. So if you like that one, and I say if you like it, because that's probably the one that if you've been introduced to this equation before this class, you probably were introduced to that one. It's very common in chemistry. However, I do want to point out that when you take a Pascal and multiply it by a cubic meter, you get a unit of joule, a unit of energy. And a lot of the stuff we're going to be asked to do in the next chapter, chapter 20, or maybe I should even say this chapter, since chapter 20 is the chapter you're working on this week. You're going to be asked to do a lot of energy. And our energy needs to come out in joules. And because of that, you probably want to be using R as 8.31. So in this problem, I don't think it matters. But in the future, when you're dealing with energy, it does matter. And so for that purpose, I like just to say, I'm just going to use the 8.31. And that way I have units in joules and moles, of course, in moles, and temperature in Kelvin. And I think that's the better way to go. Now, for this problem, maybe it's not the better way to go, because then on this side of the equation, I have to convert my pressure into pascals. So I'm going to put 101,300 pascals for the pressure because they say it's 1 atmosphere. And the other thing I have to do is convert my, I didn't leave quite enough room, my volume into cubic meters. And again, that's got to be, well, that's not a good sign.
Yeah, I think you froze again.
I froze again. Wondering if I should reboot my phone or something, or
Hunter, do you have different places you sit?
Oh, no, it's my same desk. I just sometimes put it on the corner or
Oh, I see.
yeah, I made myself a little standing desk, so I'll sometimes adjust the angle. Yeah, I always see your same bookcase too, and Mike, you've always got SBCC. So
Yeah, yeah. Okay, so when I froze, I was trying to write down this number. I was trying to write down 0.005 as the volume. So I guess the unit conversion, as long as I'm after here, is 1 atmosphere is 101,300 pascals, and 1,000 liters is a cubic meter. So that's probably worth committing to memory if you're going to be converting back and forth. We do that a lot because the units for pressure, like I said, are very common to put them in atmospheres. And also for volume, it's very common to have liters. But the sad part about that is that doesn't give you the energy in joules. So pascals and cubic meters are a little bit nicer. But your call, I guess. So anyways, turns out I think a lot of this is going to cancel out. I think R is going to cancel off, so it won't really matter what we have here. But anyways, that's my pressure, that's my volume, number of molecules. I don't really know. I know R, and I also know that the temperature starting off is 20 degrees. So that would be 293 Kelvin. And so maybe
How
again,
come
I
you
should
put it in Kelvin right away?
The ideal gas law, when it was derived,
Oh, it was in Kelvin. Okay,
was in Kelvin.
that makes sense.
Yeah. So keep in mind that, yeah, you can only use it on the Kelvin scale. So yeah, so another nice conversion here is temperature on the Kelvin scale is 273 plus temperature on the Celsius scale. So I'm just going to quickly add a 20 to 273 and get 293. And I'll just kind of box this. You can see here that we could put in to our calculator and get the number of moles if we want. And I probably will, or maybe there'll be a mathematical shortcut if I see it. But let me then continue on, because then you warm it up. Now that I've said all this, I'm trying to remember what we're doing. We're warming it up to 250 degrees. And what are we looking for? If the piston has a cross-sectional area A, how high will it rise? Okay, so now if I do the same thing, that is if I say pressure final equals volume final. I'm sorry, pressure final times volume final equals number of molecules final times R times temperature final. Now, here's where I was saying I probably could have saved myself a little bit of time in mathematics, so I think I will. Instead of actually getting my calculator out and calculating the number of moles here, I'm going to rewrite both of these equations to look like this. Final pressure times final volume over final temperature would equal the final number of molecules times R. But that would be the same if we come back to the beginning here as initial pressure times initial volume over initial temperature. And so this is the part that I was saying, if you recognize that R is a constant and the number of molecules for this particular problem doesn't change, you can take the first formula here and just write initial molecules times R as initial pressure times initial volume over initial temperature, and just set them equal to each other.
And the molecules don't change because it's in a piston, right?
Yeah, they're trapped in that
Okay.
container. So it's
Awesome.
let's see, see if they made it clear. The cylinder is closed. Yeah, see, it's closed by a piston. So they're trying to say the number of molecules are trapped inside.
Okay, so if it had an exhaust,
Yeah.
then the number of molecules would change.
Exactly.
Okay.
So as you said, an exhaust or an intake or even a chemical reaction that takes place. Now, I must admit, we don't really touch on that. I mean, having a chemical reaction is really, requiring the knowledge of chemistry, and that's really not required for this class. So
Yeah, I was just saying that because I mean I've worked with engines, so I was just picturing the piston going down and then all the stuff like leaving the piston cylinder.
Yeah, and as a side note, because we're going to do a lot of that in chapter 22, keep in mind that you don't lose the number of molecules until you open the exhaust valve. So during the compression stroke and the power stroke, we can treat the number of molecules the same. Kind of. There is a chemical reaction, but it's kind of a small change. And so you'll see that. And so I guess I'm just kind of giving you a warning that although what you say is true, the number of molecules does change. It changes on the intake stroke and the exhaust stroke, but not on the compression and the power stroke. Yeah.
Right.
Of course, I'm sure you're going to say, well, what about blow by? And okay, yeah, but kind of small stuff.
Yeah, I mean, blow by generally isn't a problem unless it's in like a Ferrari or Lamborghini.
Okay.
Then it's a problem, but those are such pristine engines that it's like they're so well taken care of.
Good. Okay, so in this problem, and I should point out a lot of problems as a little hint towards other problems is we do this a lot where we set, things that change on one side of the equation, things that don't on the other. So then later on when they change, we just bypass all the stuff that remains constants. And R is one of them all the time. So that's why a lot of times we don't really specify which R we're using, whether it's the 8.31 or the 0.0821. We just don't care.
Because it oftentimes just cancels out, right?
Yeah, because it's a constant and you're comparing a before and an after. All right, so watch this. Now, so this is where, like I said, I probably could have saved myself some time and effort here by, instead of doing this line up here and having this long discussion about what R is, I could have just put in my initial pressure. So my initial pressure would be the 101,300 pascals. The initial volume would be the 0.005 cubic meters. The initial temperature would be the 293 Kelvin. So I'm going to put that in for my initial stuff and never really bother to calculate the number of moles. Okay. Now, on the other side of the equation, here's where some thinking needs to go in. I'll start with the temperature since that's probably the easiest one. Let's see, the temperature with warming up
523
to 250 Celsius. So what's that? 523? Did I add that right? 23 Kelvin. Okay. Now, here's an interesting part of this. So I'm going to say, what is the pressure? Maybe I'll leave a little bit of room to write that. And what is the volume? And I'm going to jump over to another page here for just a second. Okay, so I'll call this page 2. And
would the volume be the same because it's the same compression and number of molecules? It's just in a bigger span. So like say it's a gas, it's just has more room to float around, but it's still 5 liters worth of gas.
Well, but it's got more room. You just said it's bigger.
Right.
That's the volume.
Yeah, never mind. Okay.
Yeah. So gases are interesting. You cannot say the volume of a gas really well because the volume of gas always takes the volume of the container. So it makes no sense to talk about 5 liters of a gas because, you know, it's 5 liters if I put it in a 5-liter container. If I compress it into a 3-liter container, it's now 3 liters. If I let it expand to a 6-liter container, it's now 6 liters. So volumes of gases are just not useful.
So density is probably more important with that then.
Yeah. And so the volume, right. So number of molecules and volume go together in density. Mm-hmm. Okay, but I guess I'm trying to draw a little picture and point out that this is the same picture they've drawn. They say the piston maybe started here and gave us 5 liters, but when the spring compressed and moved up a height h, we've now got a little bigger volume. So if I put V sub I here for the initial, which we know is that 5 liters, the new volume I would write this way. I'd say, okay, the final volume is this initial volume, which again, we know is 5 liters, but then plus this volume, which would be the cross-sectional area of the piston times the height. And so as the piston goes up, and I didn't really draw a 3-dimensional piston, maybe I should have tried to draw a cylinder where the piston can go up and there is a cross-sectional area of A. The volume that increases would be, you know, the volume of a cylinder, which is the cross-sectional area times its height. So I guess I could write the final volume as the original 0.005, and I should put cubic meters, and then the cross-sectional area of 0.01 square meters times this height h. And that's the unknown. How high will it rise? And so coming back to my page 1, right here under final volume, I'm going to put 0.005 plus 0.01 h. Hope I didn't make that too small. Maybe on the next time I write it, I'll make it bigger. But that's the new volume. Now, the other thing I have going on here is I'm going to have a new pressure. Okay, so let's talk about the pressure. So the pressure in this container right here, and so maybe I'll go back to physics 121 and say, if you look at that piston, the sum of the forces in the vertical direction would be 0 when it, you know, expands up. And so maybe over here on my free body diagram, I'm going to maybe just draw this piston and look at the forces. So what is pushing upward is the pressure that is in this now hot gas that I warmed up. What's pushing down, I would say there's 2 things pushing down. One of them is from the spring. I've now compressed the spring. And the other one is the atmosphere.
You froze again.
Oh, bummer. Okay.
You know, out of 4 years of going to SBCC, I think I've only gone to the beach like once when I was living down there.
Oh
I
man,
mean,
you're
you're,
missing out.
you're a true student.
I mean, I should rephrase that. I didn't go to the beach for like beach days, but I would go at sunset, watch the sunset, and then just leave
Yeah.
right after.
Yeah, yeah. Okay, good. Or, yeah. Clear your head, go for a walk, but
Hmm.
not a whole day of surfing and hanging out. Okay, so I think I froze kind of right here where I was trying to say that to continue on, we got to go back to physics 121 and look at the piston. Now that it has been pushed up, it has been pushed up by the pressure that is inside of the container. And what's pushing it down is really made out of two factors. The first factor is the spring, now that it was compressed. And then also the original atmospheric pressure that was pushing down. They said it was 1 atmosphere pressure pushing down. And so that's got to be included.
Are we
And
ignoring,
so,
are we ignoring the weight of that head, piston head?
well, I would say that the weight of the piston head and the atmosphere together made the 1 atmosphere that it was originally at. Yeah, so I'm not going to say I'm ignoring it. I'm going to say that when they originally told me it was 1 atmosphere, they were telling me that the combination of the weight of the piston head and the air on the outside is 1 atmosphere. Now, usually we just say the air on the outside is 1 atmosphere. So in that sense, we'd say, yeah, we're ignoring the weight of the piston. And normally that's pretty realistic, given that 1 atmosphere pressure is actually quite a bit compared to the weight of a little piston.
Isn't it like really close to like 14.7 psi, which is what Santa Barbara's at, basically
What?
sea level?
Yeah, and so right, so 1 atmosphere of pressure, you could write that. The easiest way to write it is 1 atmosphere, but another way of writing it is 101,300 pascals. Another way of writing it is 14.7 psi. Another way of writing it is 760 millimeters of mercury. Another way of writing it is 76 torrs. Another way of writing it is approximately 1 bar. Another way of writing it is 30 inches of mercury. I think I covered them all. Okay, so so there's a lot of different units, yeah. And probably in the automotive world, they probably focus on PSI and 14.7 PSI.
Focus on PSI except for air conditioning. We use bars for air conditioning.
Ah, okay. Okay. All right. So trying to balance this, I'm going to do this little formula. Maybe I should remind you then that force would be pressure times area. Okay. So if the sum of the forces have to be 0 on this piston, what's pushing it up would be the pressure I'm looking for, final pressure times the area. What's pushing down, so minus, is the force from the spring. Why don't I just say kx for a moment, since you're probably used to that formula for the spring. And then let me say minus the atmospheric pressure, which is that initial pressure and its area. That has to be 0. Okay. But you are hopefully seeing that the amount of the compressed spring, this X, is the H. That's what went up. That's where the spring got compressed. So if I put in my numbers here, I would have final pressure. And if you'll let me just do a little quick step of mathematics, I'm going to put KH over on the other side. I'm going to put plus initial pressure times area, and I'm going to divide by area. So when I put in my value of my spring constants, 2 times 10 to the, what did we decide that was? A third. And then there's the H over this area, 0.01. And then this one, the second term, the two areas would cancel off. And I would just have that initial pressure. And again, I'm going to use the pascals. And so that's 101,300 pascals. And maybe if I simplify this a little, this is times 10 to the minus 2. So this becomes 2 times 10 to the 5h plus 101,300 becomes my equation for the final pressure. All right, so back to page 1. I could write down, and I really didn't give myself enough room, so I'm going to expand this out, but I'll write it real tiny at first. 2 times 10 to the 5h plus 101,300. And if you can't see that, I don't blame you. Let me write it big. But the idea here is I now have an equation that just has the variable h in it, and now I can solve for h. Now, sadly, it looks like it's going to be a quadratic equation. But
Where'd you get the 10 to the fifth? 2 times 10 to the fifth.
oh, back here I have the k value, 2 times 10 to the 3.
Oh.
And then I'm going to divide it by 100th.
Mm-hmm.
So that's putting
So
2
2
more
decimals.
zeros.
Okay, cool.
Okay, so let me then write this in a better form that you guys can see here. So let me take this equation from page 1 and write it here on my page 2. I'll start with the hard stuff to see. So this is 2 times 10 to the 5h plus 101,300. And then this is the 0.005 plus 0.01h equals. And for this one, I'm just going to put all my numbers together in my calculator, and including moving the temperature over to the other side. So this would be the 101,300 times 0.005 divided by 293, and then bringing over the 523. This comes out to be 904, and I'll just do one decimal place, so 904.1. All right, so now I have a little bit of algebra to do. And let's see my algebra here. So I'll do the FOIL. So this becomes 2 times 10 to the minus 3h squared, I believe, because that's minus 2. Then I'll also do this one. So this would be 2 times 10 to the 5th multiplied by 0.005. So that is 1,000 H. Then I'll do this one, which 100th would make 1013 H. And then this one, which this must have been the number I just did, right? That'd be an even 1,000? No, that is not an even 1,000. better do that. 101,300 times 0.005 is 506.5. And remember that equals 904.1. Okay, so now I have this quadratic equation. Let me just write this as a 2000h squared. Let me write this as, if I add these two h's together, that's 2013 h's. Oops. I was going to put a plus, but let me bring this over, because this would be the 506.5 minus 904.1, give me a negative 397.6 equals 0. All right. So moving on to page 3. I then would have a quadratic equation. And the quadratic equation says take the opposite of the b term, that's 2013, plus or minus the square root of b squared, 203 squared, minus a 4 times the a term, that's 2000, times the c, which is a negative 397.6, all over 2a. All right. Now, of course, mathematically, that gives us two answers. And we could talk about the meaning of a negative h, but that's the one we can rule out and say we don't want. We don't want the negative h one. We want the positive. The way I defined h as positive as it's going up, and negative h would come down. I say that because as I look at my numerator, this right here is obviously a hair bigger than that one, because we've got that same number here squared, and then with the two negatives, we're going to add a little bit to it. So that would tell me I want the one with the plus sign. Also tells me the ones with the two negative signs come out to be negative. So I want the one with the plus sign, and it goes with that negative sign, and that's going to give me my h. So grabbing my calculator here, I can go the 2013 squared. And if you'll let me just put the two negatives together and call it a positive, 4 times 2000 times 397.6. And now taking the square root of all of that. And of course, it's plus or minus. And as I just argued, I want the plus one. All right, so I've got the plus one. I'll combine it with that one. So minus 2013. And then finally divide that by, and I'll just call that a 4,000 in the denominator. I get a height of 0.169. And to save me a headache, I haven't been writing in my units, but I hope I made it clear way back here on page 1 that I was putting in H's as meters, probably more clear on page 2, where I had volume in cubic meters and I had area in square meters. So H needed to be in meters. Hopefully it was also clear when I did the spring constant. They said 2 times 10 to the 3 newtons per meter. So H, and everything I've done, H was in meters. So that's how many meters. And I don't know if it's needed, but maybe the last step, then I'll just put an answer in centimeters. So looks like it's going to move up about 16.9, roughly 17 centimeters. And that was a little involved. So quadratic and a lot of stuff. Let me jump over to some solutions here.
One reason why I got this calculator is it can't graph, but it has the quadratic function already built into it. So you just put in all three constants and it gives you both answers.
Okay. Okay. Oh, good. And I got the same number as the author. Uh, okay. Be careful though. That can make you kind of weak on solving quadratics. Well, man, I don't know. It's
Yeah.
in one sense it makes you strong because you're going to get it. In the other sense, it makes you weak because you're like, oh, how do you do it? Oh, I just use my calculator, so I don't know. Yeah.
Yeah. Luckily though, it's over the years, it's just been burned into my mind. So
Okay.
I don't
Yeah, and
think it's
actually,
a
that's probably the
formula.
best thing is, is get it burned into your mind first, and then in practice, especially on the job, you're just going to put in the numbers. You need a number to move on,
Mhm.
and say, okay, let's say somebody was asking, how much it's going to move, and maybe this movement triggers something, or there's some kind of sensor, this is some kind of pressure sensor. You got me on automotive. I don't know. So maybe this is the indicator of the intake manifold pressure gauge. How much did it move? Anyway, so that triggers a rheostat, which tells the computer, hey, this is what the pressure is. Blah 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 blah. Anyways, I don't think I finished the problem though because there was a part B, wasn't there?
Yeah.
Oh, what is the pressure of the gas? And that should be pretty straightforward now because we had this equation on page 2 that we had worked out for the final pressure. So this would be 2 times 10 to the 5 times the height, 0.167 in meters, plus the 101,300. So we've done the hard stuff. So 2 times 10 to the 5 times 0.169, add to that 101,300, and I get 135,100, and I'm working in units of pascals. If I divide that by 101,300, because I think the answer may give me it in atmospheres, this would be 1 1/3 atmospheres. And just because you brought it up earlier, Danny, I'll go divide by 100,000 makes it 1.35 bars. And, well, .7 for PSI. So this would be 19.6 PSI. And I'm just having fun now. See, I don't doubt if they're going to be in PSI. But all right, let me jump over to the author's solution. And he has, pascals. And so he has, 135 times 10 to the 5. Actually, maybe I should have, because this is common on gauges. Pascal is a small amount. So most pressure gauges are listed in kilopascals. So it'd be 135 kilopascals. I know the gauges we all have in our lab. Actually, the one I used for the lab, was that this week's lab where we did absolute zero and the air thermometer? Or was that last week's lab?
Last week's lab was complex wave, so it must be this week.
Yeah. Okay. Yeah. So this is the first. Yeah. So this is the first week on. Anyways, and so you might not have done it since it's not due till Sunday, but in that one, I grabbed a pressure gauge and I debated in my mind which one to grab because we have some that read in kilopascals and some that read in PSI, and I noticed that the since you guys were going to see it on a video, the biggest one I had, I'm going to go with the biggest one, and sadly, the biggest one was in PSI, so you'll see me using a gauge that's in PSI, not in kilopascals, and I had to fight with myself because This was a big 4-inch gauge, and this one here was a 2.5-inch gauge. And I go, man, they could see this one better, but it's in PSI. Oh, but this one, it's going to be hard to see. But I ultimately, when I filmed it, I went with the PSI. I go, all right, I'm gonna go with the bigger gauge so they can see it better. All right, good. So that was some good problems. Let me jump back over to the Zoom here with you guys and turn my chat back on. Oh, you know what I want to do? Let me just go from a full screen size. All right. All right. So then, Hunter, you're asking about 47. Well, unless you guys have a question on that, I'll shift gears here. And so chapter 19, number 47. Yeah, I kind of wondered if questions would be on the latter part of 19 today or on the beginning part of 20. I know we're in 20, but it seemed like probably because of the test and the shifting gears and your other classes, seemed like we only did the first half of 19 with the questions last time, and some of these harder ones weren't really addressed. Anyways, so you are now. I say that for you, Daniel, because you said you felt like you were behind, and I guess technically you're behind, but you're probably about normal, so you're normally behind like everybody else. And that's just kind of, I mean, maybe the best advice I can give you guys, students, as you struggle through that is, you know, that's just something you guys got to get used to, is learning to always feel like you don't completely understand and that you're always behind, and you and everybody else, and you only get to go to the beach to watch a 10-minute sunset, you know. And if you learn that attitude, you got the right cultural mix to succeed in this field.
Yeah, when I was in the math lab, one of the most kind of like reassuring things is hearing other students say, "Oh, I haven't started the homework yet either."
Yeah. So it's, you know, that's what's really good about either the workshop or this Friday Zoom is there's just something about, you really just got to set up and understand this culture that, you know, Friday nights are catch up on your homework. I mean, if you want to get together with friends and do it as a group, fine, but it's not for partying. It's for catching up on your homework. In fact, I'll tell you a fun story, and I probably said it in the video lectures because it's one I like to tell students, but can't hurt to say it again. You know, when I was a student, and over the years, you know, especially by your senior year and into graduate school, you just became more and more studying. That's all I ever did was study. And weekends, holidays, these weren't time to relax. These became times to catch up because I was always behind. So, you know, I had been going through school for years, you know, between college and graduate school, I was 10 years. And I never even thought about what a holiday is. I mean, actually, technically today's a holiday. So, but it's pandemic, holidays are different in another reason. But holidays just were just out of my knowledge. I didn't know what a holiday was. I mean, a holiday was this chance that, hey, I finally get a chance to catch up. There's no lecture, there's no lab. I can catch up. Well, after I graduated at my first job, so I graduated in June, started at Boeing late June. What was very different right at the very get-go is I was used to taking my work home with me. You know, it's called homework. You know, you do a lot of work at home. Well, since everything was top secret and classified information, nothing was allowed to leave the plant. So as I was getting into gear and I joined this team and I wanted to, you know, learn what's going on, I was studying like crazy. But, and you know, when the afternoon came around, I thought, okay, I'll just take my books and my stuff and I'll head home. And I'm like, nope, can't take anything home. So I just ended up staying there, you know, and it just became my new home, if you will. And so, 9, 10 o'clock. Then I'd finally leave. But anyways, what I'm getting at is the 4th of July came around. So the 4th of July came around and I said, oh, great. What a great day to go in early, get all caught up. This is my normal mode of operation for a holiday. And I got to the plant and it was all locked up and I couldn't get in. And I begged the security guard and he said, nope, we are closed. It's a holiday. And I'm like, what? Holiday? I got to catch up. And they're like, nope, get out of here. And I was living in Santa Monica at the time. So I went down to the beach, rented a bike, had a blast. Spent all day riding along the beach trail, went from Santa Monica down to Hermosa Beach. It was about a 20-mile ride and back. And it was like, this is what holidays are for. So you'll get holidays, but not till you graduate.
Understandable.
Yep.
So
I relate to that.
All right. So on to this problem here. Okay, now that I've chit-chatting away. So let me write this one down to let's see, this is number 47, starting at 10:58. Okay. And let me find it. Switch over to the homework. Number 47 must be a little further down. 47. Oh, it looks like a thermal expansion here. Yeah, this is a big challenge making roads. It's amazing how little a thermal expansion can really lift up or buckle a road. It's for you civil engineer people. This is and walls. This is such a challenge. But watch this. It says two concrete spans of 250 meters long. Now are they saying they're each 200? No, I think the total, right? Yeah. So two concrete spans of a total of 250 meters is kind of shown in the picture, are placed end to end with no room allowed to expand. So if you were to, put, in this case, concrete without an expansion joint, didn't make my drawing even, but you need an expansion joint. It's usually just kind of this rubberized spacing between our pours of concrete, or if we bring them pre-poured, as we set them in there, we got to put some spacing between them, because if you just bring them in and what's called a butt joint, and you just lay these right next to each other, when they warm up, they're going to expand. And if they're laid against something else, like either more poured concrete or maybe the mounting joists on a bridge, they are going to expand and either crack, or if they can't crack, if they're that strong, they'll expand and one or both will buckle up because they need that room to grow. And that's what's going on here. So it says if the temperature increase of 20 degrees occurs, to what height H is the span's length and will it buckle? Okay, so let me just look at one of the concrete pieces. The original concrete piece would then be 125 meters long. And of course, now if it expands, it's going to grow a little bit. So maybe I'll draw the second one, and maybe just to indicate its original length. And then there'll be a little bit of expansion, which we've labeled here in this chapter as delta L. And so as they get hotter, the molecules move faster, they bump, they hit harder, they'll need more room. So we called this alpha for the linear expansion coefficient times the original length times the change in temperature. So in our case, since we're working with concretes, and now I need to call up the book here, or if not the book, some other device here. Let me go to my textbook. Here we go. Survey is my go-to, but I'm going to assume it's also has these same numbers listed in the OpenStack one. And let me just scroll down to chapter 19. And it's either, there's a couple of tables here. Here it is, table 1. And looks like the bottom one is concrete. It says concrete expands 12 times 10 to the minus 6 for every meter for every degree you warm it up. So that's what the expansion coefficient. It's telling you basically how much 1 meter would expand if you warmed it up 1 degree. And that's why we got to then multiply it by the 125 meters. And we also have to multiply it by the increase of 25 degrees Celsius. Maybe I should have put my units. This would be meters. This would be degrees, inverse degrees Celsius, so that we're going to be left with meters.
It says the temperature increase is 20 degrees Celsius, I think.
Oh, thank you.
Mhm.
For some reason, I was thinking 25. Let me come back. Yeah, 20. Okay, thank you. All right. All right, so we warm it up 20. So we don't know what we really start at. Doesn't really matter. It just warms up 20. And so if I grab a calculator, that tells me how much bigger it is. So 12 times 10 to the negative 6 times 125 times the 20 means it increases by 3 centimeters. So it's not much of an increase. Which, like I said, you could put a little rubber piece in here that's just 3 meters thick, a little more than an inch, and it would, expand into it. Although an inch is a pretty big gap, I would just make my concrete less big here, maybe cut that in half, and then my expansion joint would be half. And that's the way the road should be designed. And so maybe it's 50 meters long before there is a crack or an expansion joint before you go to the next one. Okay, but that's going to be the expansion. But since in ours, then we're going to have something that looks like this. We're going to have a expansion that buckles up. And of course, our problem is trying to find out this y, how tall is it? Because I suppose you could argue that if y is not a big number, you could just build the road this way. Don't worry about expansion gap. On a hot day, it kind of buckles up. So what? Somebody can just drive over it and it's not that big of a deal. Or is it a big deal? Let's see what kind of number this is. Because if this is 1 meter, we don't want to have a bump in the road that's a meter high or a half a meter or even 10 centimeters high. That would just be
Do you
too
think
much.
that kind of happens with CC's bridge where it just heats up and you kind of see a little bit of a bulge in the center?
Yeah,
like
yeah.
During summertime?
Oh, yeah. Yeah, this is easy to see around buildings and bridges. Many bridges actually underneath have a little marker for the engineers to inspect. They, have, maybe it looks something like this. One side of the bridge is mounted to the ground, and the other side of the bridge is put on a rocker mechanism. And then underneath is a little pointer device. One side of the pointer is on this and the other side's on the rocker, and so it shows how much they've moved past each other. And so you can climb underneath and kind of see the mechanism. A lot of them do this. Our building, usually when I'm talking about this, I could right outside the door at the lecture hall, because technically the building is two pieces. The lecture hall is on the left, and the rest of the building's on the right. And what they do is they put like a little metal piece that extends over the joint. So if you're on the outside, all you see is a metal plate. You can't get your fingers in there or put any debris in there. But you could see a difference on a hot day and a cold day where this metal plate is and how big the expansion joint is. And then on the top of the building, it's same thing. They got to make it a little more waterproof since the rains come in. But so it's harder to see on the top. They've got it covered. But on the side of the building, right where you just go in the door to the lecture hall, it's just a dead giveaway. Bridges are kind of neat, where they'll often do this too. Instead of putting it on a rocker, where my picture of a rocker, maybe they'll do something like this. The first half of the bridge is anchored, and the second part is anchored, and there's an expansion in the middle somewhere. But instead of just leaving an open gap where tires can get in there, they make something that looks like a saw blade, and it makes like this on one end of the bridge. And so if you're on top of the bridge, you would see something that looked like that. So as the tire goes over, there's never a gap for the tire to really fall into. And then it expands back and forth on a hot and cold day. And so on a cold day, when the things shrink, it'll look like this. And then on a hot day, it'll kind of close up. But on a cold day, you can actually, when you go over the bridge, you'll hear more of a thump thump. You go thump thump, thump thump as you go over the bridge. And on a hot day, you just right over the top, and you don't really hear the thumping. Actually, trains are really good, because I'll often hear the train, because I'll commute up pre-pandemic on the train here from Ventura. And on the cold mornings, the rails pull back, and on the mornings when the train goes, you can hear clackety clack, clackety clack, clackety clack, clackety clack. And then on the hot afternoon coming home, it just smooth ride, no clacks. The gap kind of closed up. There's still always a little gap, because they've designed it for really, really hot days. So unless it's really extremely hot, the gap doesn't completely close up. But the sound is a dead giveaway how big the gap is as the cars go over or the train goes over.
Cool.
But on roads, you can tell. On hot days, sometimes I'll notice going down the freeway, thump 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 thump. And so there is a little buckling in the road. And then cold days, it's not there. All right, so back to this problem. So this is a 125 meters across the base of the triangle. And now that it expanded up, it is now 125.03. And again, I know you're going to say, well, that's not much, but the third side of a triangle is actually quite a bit. This would, using Pythagorean's theorem, this would be 125.03 squared must equal 125 squared plus y squared. And so we can figure out then what the height of this buckle is. And so grabbing my calculator, I'm going to go 125.03 and square it and subtract off 125 squared. And now take the square roots of this, and this would actually lift up an amazing 2.7 meters. And like I said, it's just kind of the way geometry at an angle is. The hypotenuse isn't much longer, but if you don't put just a small amount of gap, 1 inch in the gap of that road, instead, this would expand up, almost, well, it'd be the height of a typical room. So obviously that'd be too much for a car. You don't want to be driving down the road and see a buckle in the road that's the size of a wall.
And that's
A little nose
just
in your engine. You can make it.
Now it looks like it's angled up, so it's really more of a ramp. So I guess maybe we could make it. Yeah, this wouldn't be like a big thing. If it actually did go this way, it would just be kind of an uphill climb, going uphill about 3 meters and then downhill. So on hot days you would have an uphill climb, and on cold days it'd be flat. So, but it would lose its support underneath and crack, and you just, as far as I know, you don't do it like that. You actually put expansion joints in there.
that's crazy though. Only from 20 degrees.
Yeah,
Yeah.
yeah. And it's just the nature of the the geometry and it's set up. I'm just checking the answer because that just seems too big to me. But yep, there it is. So that same number. It's crazy. I'll throw another one in here too. Just kind of a fun. It's the same geometry, but I came across it years ago when I was taking a sailing class. We were, and so a sailboat looks something kind of like this, a tall mast. And when you go to hoist the sail, the sail is sitting down here on the deck, and there's a line that goes over the top of the mast and comes down and grabs the top of the sail. Okay. And our instructor told us that the sail is really heavy. He goes, this it probably weighs more than you. He goes, it's about a 200 pounds worth of sail. He goes, and so if you try to pull on a force straight down, you're going to have to pull with a force of 200 pounds in order to lift this sail up, which is 200 pounds. Actually, at first he didn't say that. He just said, don't pull straight down. He didn't explain it. He just said, do this. He said, take the mast on your sailboats and run the line over the top. And when you get down here, you'll notice a little cleat. He said, wrap the line around the cleat and pull sideways on the line. And that will lift up the sail. And I heard him say that, and I go, oh, no, wait. You're crazy. I want all the force in the direction of the lift. So after he explained it, I got on the sailboat, and I pulled this way. And sure enough, the only thing that happened is I lifted myself off the ground. And I was actually lighter in those days. So I was probably about 160 pounds at that time. And I just went up, and the sail never moved. I mean, it moved up a little bit until I got most of the sail off the ground, because then it equaled my weight, 160 pounds. And I couldn't get it any higher. And I was fighting and pulling, and I was trying to hook my feet on the deck and grab something with my legs so I could pull harder. And the instructor comes over and he goes, and he just looks at me and goes, dude, I told you, hook it to the cleat and pull sideways. And I was like, All right, I don't see how that's going to work. So I wrapped around the cleat and I pulled sideways and it went up with one hand. I just pulled that thing with one hand and said, what the heck? And then it made me come home and think about this geometry. And so if you think about this geometry, if you have two vectors, and I'll use the same numbers, if I only pull with a force of 2.7 pounds on this direction, that means this direction would be the 125 pounds. Now, of course, to balance it was why you needed it tied to a cleat, because then it would be coming back at 125 pounds that way. So by tying it to that cleat, I was able to get the 125 pounds from the cleat, and I only had to pull with 2.7 pounds. And of course, I had to go more because to get up to 2, let me just double it. So if I doubled this to say 5 pounds, so if I pulled with 5 pounds, this would be pulling down with about 250 pounds, and I usually just lifted it up. And so all I did was wrap it around that cleat, pull. Then you got to take in the slack and wrap it around the cleat again and pull and wrap it around and pull and take in the slack. But this very heavy sail I could lift up with one hand, where one hand was pulling sideways and one was wrapping around the cleat. And I was like, okay, this is brilliant. I like physics. This is so cool. And then it really helps. Couple of years later, we were out riding Jeeps and got stuck in the mud. And we had this little winch on the side, and we pulled another car up alongside and turned on the winch, and it still wouldn't get out. And the wrench was pulling with some tension. We're like, oh, crap. Then it dawned on me, wait. And so the three of us stood on the side of the cable and pulled sideways. And even though our wrench was rated at something like 2,000 pounds, we pulled this way, and somehow we got more than 2,000, and we were maybe up at around 3,000 and pulled it out by pulling sideways. So we pulled sideways, and then the wrench winded up, pulled sideways, pulled sideways, and we were able to get far more than the machine could do. And it's like, oh yeah, we're free. So I've never forgotten that. And I've seen people do this. I've seen people practice this little, I don't know what it's called, where you take a rope, or it's really more of a ribbon, and you tie it between two trees and you walk on it, or a hammock. But you don't want to pull that thing tight, because if you pull it tight and you pull down with your weight, say 200 pounds, this could be something like 3,000 pounds in this direction, and easily snap the rope or the line. So you do want it to have some slack in it so that your angle is more, that's probably extreme, but maybe not that much slack. But
Are you talking about the slack lining where you see people
Yeah.
like bouncing on this like
yeah,
line?
yeah. So the slack line, but if you start with a tight slack line and you put your full weight on it, you could snap that slack line real easily. Amazing how much stress that is. So you want to keep it a little loose, so when you get on it, then it changes the angle dramatically. Because technically, I know I got sidetracked in all this, but the reason this worked was because of that small angle here. If you had a triangle that was a bigger one, like say 30 degrees, then this here is half of the hypotenuse. So the tension in the line is only double. So if you leave it loose, so you get a 30 degrees and you weigh 200 pounds, then the tension in the line is only 400 pounds. And that's very reasonable for those slack lines. Yeah, they're pretty strong because they're a ribbon. Yeah.
Yeah. I saw this guy, like I went on a hike, and it was like a hike that went out to this cliff that looked over the ocean.
Okay.
and there were like trees on either side of the cliff, and this guy had a like safety harness that he just hooked to the slack line, and he had the slack line going over the cliff, so he was just like bouncing up and down just over the cliff. That like if he fell off, probably would have killed him. So he just put a little safety line on and was having the time of his life out there.
Yeah, yeah. That's why they do it, right? Yeah. That's the thrill, but with safety. Like hopefully a roller coaster, you know. There's something about that thrill, but hopefully it's all designed right and engineered right, and there really is no safety issue, and so.
Yeah, roller coasters are less fun when you die. So.
All right, good. All right, so here let's I'll jump back over to the Zoom here. And see if there's anybody else. No other question yet? Okay, well, I got that.
What do you do with all the paper that you make, like do all these problems on? Do you just throw it away, or do you have like a whole pile worth of papers you did?
You know, I started recycling them. I starting in this pandemic last spring, I started making a little folder, and I go, well, you know what? So I can reference back to them. I'll put them here, and then that wasn't too bad because the pandemic was about halfway through, and I don't think I did as many videos. So I started doing the same thing last fall, and boy, between all the paperwork by doing, you know, these lectures and then the video solutions, because I go, I'll just keep them, and yeah, I just had an incredible stack of paper, and I never really referenced them. So this semester, I decided, you know what, maybe once I get them in video form, I should just trust that that's the original, and that's where I'll keep them. And so no, I haven't been keeping the forms. I just recycle them each time. And yeah, I sometimes wonder when I take out my recycle, it's just loaded with paper. But you know, now that I say that, it's really not much different than what I would do at school. I'm just doing it at home now because my little recycle bin in my office just always filled up. And like every 3 days, I would take my recycle bin out to the big recycle one by the loading docks there and pour it in. And at the end of the semester was actually probably worse because everybody turned in their homework, you know, and I had stacks of homework and stacks of labs. And I was like, okay. And I had boxes I'd have to go down to the recycle bin. I'm going to auction them off on eBay.
Yeah.
So, actually, I think I should do a better job. You know what would really be helpful is a better job of on the videos putting a tagline in there. So when people search for, you know, thermal expansion problems and examples, it would show up. Because right now, pretty much the only people who know that there's a helpful hint are those who, you know, you guys in my class who get it from, you know, my email. And obviously there's some people who don't even read that because they'll email me something and say something of effective. Hey, you should do number 7. And like, okay, yeah, I just sent you out email yesterday. I did number 7. Like, oh, okay, thank you.
I try and look through, like in a week, try and look through which numbers you've done. So that way, like when I get to office hours, say I had a question on 40, but you did that last week. So I'm like I just mark on the syllabus which ones have a video if I need the help and go from there.
Yeah, well, that's good. That's there's and obviously most of you do that because I think there's only been one time or something where I've done one during the Zoom here where I had already done.
think
Are we
last-
gonna?
Oh, sorry, go ahead.
Oh, I was just gonna say, are we probably gonna be breaking in a second? So we probably shouldn't start another one, right?
Oh, yeah, let's take a break. Especially since I ended up skipping breakfast. I was gonna do breakfast here at 11:30. So, yeah, we'll take a break and then yeah, put yours in the chat room and maybe I won't tell you so many stories next time. We'll do more.
Oh, you good, Mike?
I enjoyed the stories.
Same. All right, see you guys.
All right, guys.
In an hour.
See you in an hour.